I think we can start our today's meeting.
Okay, so hello everyone and welcome to our joint event with SPE Central Ukraine. My name is Ioana Mitra. I'm program chairperson of SPE Romania and I'm really happy to see you all here. Basically, we wanted to have a series of 2 events. So this is the first one, which will happen today. The next one will happen in 2 days. And the main topic is related to geology and to the challenges and opportunities that we are facing in the Carpathian area, which is basically common for both our countries. Today, we will have as a speaker Paul Soflau, who is working in OMV Petrom. He graduated the University of Bucharest, the geology faculty, and I know him from I think 3 or 4 years ago when he was my mentee basically during one OMV scholarship program. So he was actually in contact with the industry already from the faculty. And then once he graduated, he joined our company. And since then, he's working in the same department with me together with really experienced people from the area. So he have learned a lot in these years and he happily accepted our invitation to present us the work that he's been doing in one of the fields in the area. So thank you for joining. We will leave the questions for the end. So if you have questions, please put them in the chat or you can directly ask them once we finish. And Paul, the floor is yours.
Thank you, Anna. Hi, everyone. Thank you, Paul, for being here. I'm going to share my screen. Can you see it?
Yes.
Yes.
Thank you. Today I'm going to present you introduction to geological modeling of a field from the external flysch area. Sorry. Then I'm going to present you introduction to geological modeling of a field from the external flysch area. Before we begin, let me give you a quick overview of today's agenda. We'll start with some things about me, short things, followed by objectives and general overview of the field, followed after by geological setting, static model, the positional environment, and in the final, the conclusion, of course. A brief introduction. I graduated, as Ioana said before, University of Bucharest last year, Faculty of Geology and Geophysics. I'm working in OMV Petrom as a professional geologist since October 2023 in the Opportunities, Maturation and Execution Department. I'm building 3D geological models together with seniors with over 30 years experience in the oil and gas industry. Our field is located in Moldova region, in this place. And from a geological perspective, is located in Paleogen flysch of Eastern Carpathians, marginal fault nape. The field is a faulted anticline oriented north to south. The mean depths of we have 2 reservoirs are approximately 1,000 meters for Oligocene and 1,900 meters for Eocene, but the Eocene is depleted since 1983, I think. In the right side, we have the model of the first well from Romania that used mechanical drilling for oil extraction. A brief history of oil production in this area is nearby our field, and also natural oil according to the region at the end of 19th century, and the first extraction were carried out using hand-operated wells. After the war in 1945, drilling activity resumed, facilitated by advancements in understanding regional geology, as well as the introduction of rotary drilling and turbine drilling methods. The main objective of the study is the water injection. The water injection is going well, and the objective is to extend this process to increase the production. The injection first took place in the marginal areas of the field, and after the previous study, they continued the water injection in the middle of the field. So yeah, water injection is in our field since 1953 up to date. And we have also 151 wells active and 25 for the moment are in injection. Here we have a simplified geology map of Romanian Carpathians and also its foreland. Map features also oil and gas fields from Romania. The Eastern Carpathian Faults and Trust Belt of Romania is one of the oldest oil and gas producing areas in the world. Numerous fields have been discovered in this region since middle of 19th century. Here we have main structural phases of outer Moldova that consist of units that encounter significant tectonic activity in the Miocene. The external flysch is composed of nappes, Tarcău, Vrancea, Udea, and subcarpathian nappe. Here we have a simplified stratigraphy, the formation and map evolution of the Eastern Carpathians. This domain opened during Triassic, early Jurassic, at the west of the East European margin, and closed between late Jurassic and Miocene times. The early Cretaceous nappe assemblage of the Carpathians, Dacia Mega-Unic and Ceahlău-Severin, move north to east from sea to you can see in this image. The Cretaceous Paleogene flysch and Miocene Pliocene molasse units deposit in the narrow Carpathian foreland basin, where thrust is onto the Eastern European margin during the late Oligocene, forming a succession of thin-skinned nappes. These are known as the Moldavites. Geological setting. Here we have our layers, our main layers from this well, reference well. We have Kriva formation of Kriva 1, 2, 3, and 4. We have also this transition, upper diasodyles and lower diasodyles. Supra Kriva is also a reservoir rock transition also, but the most important layer is Kriva 1 with the best properties, best porosity and permeability, and also you can see the thickness is very good, around 100-150 meters. Kriva 2 is also have 100 meters, but he has some intercalations. Here is our field. We have unfortunately, only one 2D seismic line available. This our field is an anticline, as I said before, oriented north to south. In general, we can say that Kriva sandstones can be regarded as quartz arenites, as they have high quartz fraction over 90%. They are almost entirely composed of quartz on both grains and matrix. In addition, the sandstones are well consolidated and sorted. Kriva 1 is one of the most important reservoirs from Eastern Carpathians, and I put an image of an outcrop with Kriva. You can see often that is very titled and also has stratified layers. Now moving to input data for the static model. We have available like 400 wells approximately. We have also digital logs with V-shell, porosity, permeability. We have this sedimentologic study by Hot Engineering from 10 years ago that is based on 2 new wells that were drilled after the latest study. The main objective of this study was to provide a detailed core description and interpretation of both wells in order to achieve a profound understanding of the lithology, lithofacious and deposition environment setting. And also we have here a borehole image log interpretation also. Some core. Well, log correlation. First of all, we have from west to east. Kriva 1, as I said before, is the most important layer. It's quite continuous. It's clean, good thickness. Kriva 2 also quite important, but unfortunately with a lot of intercalations. Supracliva and transition are quite poor, but also has a few layers that are reservoirs for transition, for example. Well, low correlation now north to south. If you observe that from this direction, the thickness of the layers decrease from north to south a little bit. Now I'm diving into fault model. Fault model is based only on well data. It is observed that in this well, the eastern part of the field, we have some salt because above the Oligocene formation, sedimentation continues with the Miocene, which is represented by lagunar deposits, salt and gypsum, which provides us a seal for the reservoir, fault 1 here, with a maximum throw of around 300 meters, dipping to east. Fault model, here we have, for example, fault 5 that is not sealing, only fault 1 is a good seal for us. Normal fault in this case is around 150 meters throw. You can see here very old logs on papers. They performed tracer tests in different wells to see the connectivity between this field, our field, and the field in the southern part. We are not allowed to use the real names of the reservoirs or wells or data and so on. And I will name it, our field is named with A. This field will be named with C. Tracer performed for the first time 20 years ago, approximately. And the result was quite uncertain. We have a problem here because we have four fields that were the exploitation, were done like simultaneously, and they don't know actually how it goes with the connectivity, and that's why they done this tracer test. Here we have, as I said, with A, our field, C, the field in the southern part, B in the northern part, and D in the eastern part. Oil-water contact is the same on both fields. The connectivity would be, as I said, is uncertain. In this case, it's the same with the field in the southern part with the sea. And here we extended the main fault to the eastern part here. Structural model, as I said before, north to south oriented anticline, 6 km length, 2 km width. It's faulted by 3 normal faults in northern eastern part, layers dipping 10 grades on the west flank, 45 in the east flank. The interpretation is based on your well data. Fault 1 is the main ceiling fault. We have also fault 4, 5, and 6 that are no ceiling and does not have any impact on volume in place and dynamic model. Also, fault numbers and azimuths remain an uncertainty for us. And here we have a field cross section with our layers. Now we are diving into deposition environment. First of all, we have here a cartoon showing the positional environment model of the field. Lithology and facies of both wells represent a deep marine slope to shelf environment with turbidites and ice-affected sediments. As a result of a cooler climate within the Oligocene, probably seasonal ice might have been situated along the coastline, representing a new source of sediments. Coarse subangular grains and lithoclasts have been shed off the shelf onto the slope environment by mass flows as an effect of varying sea level. Another likely interpretation is that these angular clasts might have been trapped in floating ice and later drop onto the seafloor after melting, caused by high-frequency changes in climate. These are gross depositional environment maps, GD maps, done by Hot Engineering, that represents a simplified illustrations in order to better model geological facies and are ready to use an input for our 3D facies modeling. GD maps are a result of the full integration of all available data and therefore are constrained by wireline logs, core data, and the materials. GD were created for the reservoir layers. They split it Kriva 2 in 4 different layers and Kriva 1. Job bodies interpreted it match the regional paleocurrent direction from northeast to southwest. We'll start with Kriva 2D. The lowermost section of the Kriva formation, Kriva 2D, represents the most shallow and proximal environment and could only be confirmed by core. In well 1, the tetralitic and partly tidal-like character of the core section might be a result of the proximity to the coastline with a link to the marine environment. Therefore, Kriva 2D is interpreted as shelf environment with sand packages not representing classical turbidites, but material possibly transported into a kind of bay interdistributary channels. The muddy sections in between most likely indicate low energy periods, which are mainly protected from constant high energy events, but have, however, partly been affected by storm, creating mud rips up. Because some protection is assumed, barriers are envisaged between shelf and slope environment, although their possibility and dimensions can be discussed further. We have Kriva 2C is interpreted as the flooded version of the Kriva 2D, thus showing remaining mouth bars on a shelf to the slope transition zone. Both wells have cores in this section indicating a muddy background lithology and thin sand packages, similar to Kriva 2D, but muddier. Now we have Kriva 2b. It's a typical slope environment characterizing the interpretation of Kriva 2b interval. Using Petron's marker set, well 2 has encountered a typical submarine channel, whereas the course of well 1 reflect the muddy background lithology. According to the marker suggested by Hot, both wells would have drilled the submarine channel with a sequence boundary at their base. And the Kriva 2a is also interpreted as a slope environment with similar features as in Kriva 2b, but only occurred in well 1. According to the blocky log signature of both wells, it can be assumed that they have both penetrated submarine channel complexes, which transported sediments from the source in the northeast onto the slope and probably also further into the basin. And finally, Kriva 1. The Kriva 1, the best reservoir characteristic. Course of both wells were interpreted as upper slope environment with thick sand succession confirming the presence of turbiditic events. Furthermore, these turbidite channels partly show full cycles from the base to its abandonment to the top. At the top, perturbation is present in both wells too. Turbidite fans, as mentioned, moderate to poorly sorted turbidite fan sands of well 1 are generally coarser compared to mainly very fine to some medium-grained sands in well 2. The main component is quartz with highest amounts in turbidite fans up to 90 approximately percent. On the slope channels, the characteristics of channels samples of both wells can be summarized as follows: coarse sand to granule conglomerate, poor sorting due to sedimentary rock fragments and low porosity as an effect of silica cement. And now I'll show you a course from one of the new well with Kriva 1. The sandstones present can be described as mainly homogeneous, very fine to medium grained, highly fractured and strongly oil stained, as well as either cross bedded or a massive like in C here. From A to C, we have argillous sand to siltstone overlaying medium grained hydrocarbon stained sandstone, which are partly topped by the mudstone intervals. And in D, we have mud dominated bioturbative overlaying low angle cross bedded silt to sandstone. In A here, we have argillous sandstone with muddy rip-up class overlaying medium grained heavily hydrocarbon stained sandstone. In B, we have turbated low angle cross bedded sandstone with possibly clay drapes. On C, we have a section with completely fractured, maybe black mudstone. Now we have the positional interpretation. This is done by hot engineering from the left, and this is our interpretation. Before electrophases is a very detailed interpretation, each piece of core in electrophases, but before that they how to say it, define the fascias on different classes from here class 1 is a very good reservoir to non-reservoir fascias like in class 9. After that, they calculated the electrophasia was the sign to specific deposition environments according to the deposition line concept. Because we don't have available so much data for all wells, we divided into just 4 classes to compare with what they did. We applied cutoffs for V shales and we separate bad and good scent, good properties. Here is our 3D model. We try to replicate somehow what hot engineering done. Turbidite fans with slope channels, and mouth bars. Now we have 3D grid up setup and layering. Together with the reservoir engineer, we create a horizontal grid. The main idea of this grid was to integrate each well in its own cell. That will be easy. It will be much easier for the reservoir engineer to do the dynamic model in the near future. Here we have our anticline, our field with the wells. Property modeling. This is our data for the input logs, modern ones, vintage ones. We have, unfortunately, just 11 wells that are more complex than vintage ones. We have course. We have also production tables, old reports, and so on. Due to uncertainties, multiple porosity and permeability equations were created. In this case, the one with yellow, and the one here with red were tested, and was good for the simulation. Was tested by our engineer. Property modeling. The facies model was built based on electrofacies. We have this model only for Kriva 1 and Kriva 2 is the intervals with most interest. And the clay model was created based on the volume using the depositional trend model from HOT and the facies model, but as I said, only for Kriva 1 and Kriva 2. Then total porosity model was constructed to input total porosity log using the CGS co-creaking method with the clay volume for population to populate the model. Permeability was derived from the permeability logs, also using the same method as the previous one. Property modeling also from saturation high function modeling. We have this from the petrophysics. We describe 6 type of rocks, rock quality index from the high saturation. This one with red, and with blue we have rocks with bad properties that are non-reservoir. Based on this, reservoir engineer created the capillary pressure curves that we used to initialize the dynamic model. We only use, as I said, Kriva 1 and Kriva 2 because are relatively sharp, or I don't know, massive and clean. Dynamic modeling. Our study is ongoing, so we have a lot of things to do in the future. Production, the reservoir analytics and material balance, to evaluate the current performance status of the water injection to divide the field structure in segments for multi-tank material balance, to calibrate the segments to average historical pressures, to identify the communication between the segments, with respect to oil and water fluxes, perform water flooding, conformance analysis to identify the best and less also optimized water flooded areas. Also to integrate static modeling, dynamic modeling with intersect. Use the understanding gained from the previous work package to calibrate static and also dynamic model. Perform injection and production optimization. Identify new patterns. Optimize existing production or injection scheme. And also in the finally, try to propose an action plan to verify the field. I will sum up with some conclusions. The static model was built based on well data, since, as I said, we haven't any seismic data available. The understanding of the connectivity between sands is very important for water injection process. Uncertainty and sensitivity analysis will follow up to capture a wide range of possibly property models and volume in place. Between geologist, petrophysicist, and reservoir engineer will be a loop until a good history matching will be performed. And I think the most important one is team working, because this project is a very complex one and it involves a close collaboration with team members. Thank you for attending on this meeting. If you have any questions, please.
Thank you for presentation. May I ask a few questions, if possible?
Yes.
Sure, please.
Can you go back to the slide with property modeling? Because of the quality of the picture, I unfortunately couldn't see what was on the vertical scale of the picture. There was a graphics with, that blue, red, green parts. And unfortunately, if it's not, your screen presentation is missed now. Did you cancel it perhaps? There was a graphic, and on the horizontal line we had seen a water saturation coefficient, and on the vertical was what?
Let me a second to share again.
Yes, this picture.
Yeah, this one. This one. Property modeling, you said, no?
Property modeling, the last one with this horizontal thing is water saturation, and the vertical one.
This one, yeah, high saturation here, yeah.
Mm-hmm.
And here, the high saturation and good porosity, yeah. Saturation, yeah. Did you hear me?
Yes, I can. So one of the axes is actually porosity, yeah?
Yeah.
Okay,
Porosity,
thank you.
Porosity and permeability.
Okay, I understood. And some question about actually stratigraphy and sedimentation. I just wanted to know, because you mentioned Oligocene and Eocene sediments, as they are quite similar to those appearing in Transcarpathian in Ukraine. We have it like a flysch sediment, so it's like interbedding of sandstones, siltstones, shells, and so on. And there's a problem of tracing their lateral distribution, because they tend to change in lateral direction to get replaced with some more more tight types. So during your modeling, how did you trace these horizons with more permeable properties? Because I know you used only well data because seismic wasn't available, but what helped you to trace these selected horizons? I hope I can understandably show this question because it's not like in usual horizon. Okay, usual for example, Ukrainian DDB structures, because there are very thick layers of, for example, sandstones, and we can trace them and show them in meter scale. But here our sandstone samples can be 1, 2 centimeters or even millimeters, but these thin layered sediments, they complete in total, they make a reservoir. So how did you solve this problem?
We were lucky because we have the sedimentological study done by HOT, and we have some examples, and we correlate the Kriva in I don't know how to say it, with much confidence because of that. And also we have can I say it? Yeah, no, I don't know, but it's just the study done previous, and also the materials we have received from the past studies.
Okay, see, and another question was quite close to it and related to the channels you showed on a few slides back from this one. And if there is no seismic data available, so you cannot trace any seismic phases, any seismic sequences, perhaps you can tell some like details, share experience, how these channel phases can be identified in well logs, for example, in core and so on. Because, for example, we can have turbidite sandstones, and also we can have sandstones of different origin, not related to turbidites and all these processes. And how can you define them, separate them one from each other?
In this part, I was lucky because I work with a very experienced geologist, but I also read the history of this area, and also as I said before, the sedimentological study helped us a little bit, but I don't have an exact answer at the moment. I can check and follow up with you additional information if you want.
Thanks.
I'm nervous, sorry.
Okay, and perhaps the last question, perhaps someone else wants to ask something. I see you used Petrel software for most types of work, but for depositional model and, okay, for example, well interpretation is definitely shown in Petrel. All these horizons, for example, or not horizons, but surfaces we can see on the current screen, I see they're also done in Petrel. But
Yes.
which perhaps additional software were used except Petrel?
I only use Petrel, but petrophysics, the petrophysicist used the interactive petrophysics, and the geological engineer used how it called
Eclipse.
Eclipse. Thank you.
You're welcome.
Okay, thank you for answering.
Thank you too.
Hello, Dimitri. I have a question. Thank you for.
Yes.
Can you hear me, right?
Yes.
Just a simple question about geology part. Could you please move back to the one of the first slides, your presentation, and where you can see some geology structures? Yeah, like the first one. Yeah, just
Yeah.
like this.
This one.
Yeah. Actually, I'm from Ukraine, and we also have lots of fields in Carpathians.
Yes.
The Ukrainian part of the Carpathians, and of course we have outer and inner units there. And our fields are located in the company where I work are located in the inner part, and there are lots of over thrusting faulting systems, I would say. Like there is no or lack of normal faults. Majority of them are reverse or even over thrusting. So my question is, have you had the chance to model such kind of complicated fault thrusting systems, or you are just working with the normal faults when you create your grids?
With the normal ones.
Sorry?
With the normal ones.
Okay, so you're working just with normal faults, and you didn't have a chance in modeling with these like over
No,
trusted faulting system. Okay,
for the moment, no.
okay, thank you.
Thank you.
Hi, Roman. May I ask you why you are asking about modeling this type of faults? Because I, for example, it's not really in the Carpathian itself, but it's a bit more to the south of Romania in the Getic Depression. And in there, we had the chance to work also with reversed faults. So if you have any specific question, maybe I can help you with the answer. What we do in general, it's either we work on smaller scale, let's say just at the reservoir level, we cut the entire section, and we, for example, in a series of, I don't know, 10 elevation, we only work with 5 elevation, and basically in that area the faults are uh, straighter, to put it this way, and easier to be modeled in Petrel. And when we have more complex type of faults, we use pillar gridding in order to make the model look nicer and more geological in terms of how we basically use that into the software itself, if that will be a bit helpful for you or related to what you are asking about this type of reverse faults.
Yeah, thank you, Jan. Actually, I asked that because in our part of the Carpathians, we have lots of fields which are characterized exactly with such types of faulting. And when you work with pillar gridding, with pillar grids, it's quite, I wouldn't say impossible, of course not, but it's really difficult to reconstruct, to build such kinds of grids with, like if we have just one reverse fault, it's okay, no problem. But I'm more curious, what if we have lots of such types of overtrusting system of faulting, and how is your experience in incorporating them into the grids? And because it's not so easy for us, we are experiencing lots of issues with that. Even we are trying to do not like pillar grids, we are trying to do like structural framework approach,
Yeah.
generating the depot grids, etc. But it's quite cutting edge technologies, and we are just on our way to do that. So I just asked about if you have these complex faults,
Yes.
and there are lots of them. How do you work
Yeah,
with
so
them?
for this one, like I said, we basically just cut the model for just a specific interval in order to not have them overlapping too much. We try to basically use with stair-step faults, which is not actually the nicest one, but still sometimes that help. We manually editing a lot around the area of the faulting, and indeed for one of the project, but I haven't done it myself, but we have colleagues with which did that, was actually also using what you were mentioning, this structural framework, and actually looking more nicer than the other one. So it depends from area to area, from geologist to geologist, because some of the fields are easier, some are more complex, and indeed sometimes you do have a lot of challenges in actually building the structure first that looks properly. But for sure, if the structure is complicated enough in terms of faulting, then it will be even more complicated in terms of simulation, because there, when you have twisted cells and all this stuff, even bigger problems are popping in.
Yeah, it is. Thank you.
Thank you also.
Thank you for the presentation. Actually, I would like to ask a question that I just posted in chat about some energy transition project. Just what I mean, if there was like indicated some high content of helium or hydrogen in the gas production wells, in the gas composition. Also, like about geothermal gradients, just in the Carpathian region. So, like which one you can see, and yeah, maybe that's all. Thank you.
Thank you for your question, but I don't have a proper answer for you at this moment. I'm sorry.
No, it's okay. Just like many companies, like some international, just started exploration activities for hydrogen or helium. That's why I'm asking. But just like not many companies are doing that. Thank you.
Thank you.
Any other question from the audience?
I also have one question, hello Paul, related to the property modeling that you performed in the project. I saw those models that you created, and I'm just curious, which algorithms did you use to model the property, the electroflashes, from one of the slides? I don't remember the number of the slide, but if you'll scroll down, there was a comparison of the models, porosity. Okay, the slide number 30. Maybe you mentioned it in the presentation, but I just missed. So I'm just curious which algorithm you used for property modeling. Is the Kriging simulation something specific?
Yes, the Kriging, yes.
Okay.
Kriging simulation.
Okay, thank you.
Okay.
And just the last question, and the data analysis, have you performed it somewhere, or you did it in Petrel, or you just took some data from the open literature sources or something?
Data available.
I mean, the data analysis, the variogram parameters, the transformation of data if required.
From also from previous studies, from Petrel also, and also from the documentation. Sorry, from all parts.
Okay, thank you for the answer. And thank you for the presentation.
Thank you. Thank you for the question.
I guess we have one more question in the chat.
I think it's the same question which you mentioned.
Okay.
And the other two are just some replies from another geologist from Romania to the question that Roman
Okay.
had
Okay,
related to
great.
the faults.
Thank you.
Okay, so if there are no other questions, I would like to thank you, Paul, for presenting this. Thank you all for joining this event. Thank you, SPE Central Ukraine, for organizing the Zoom link and everything. And hope to see you all again in 2 days to actually see also what's been done in your country, which will be for sure of interest for all of us here in Romania. So thank you, everyone. And if there are no further questions, I hope to see you all in 2 days.
Thank you.
Thanks for your participation. Thank you for your questions, and hope you will see the next sessions as well. Thank you.
Thank you.
Thank you.
Okay, bye.
Thank you.
Bye.
Bye.
Thank you. Bye.